Hello, my name is James, and welcome to BC Geology. This episode, talking about the geology of Stanley Park. Now, behind me right here is a contact point. To set this thing up, there's a couple layers. Behind the camera is mountains. These are granite mountains formed by ancient magma chambers that have been cooled and they've been forced up here, and we got mountains. Then there's a sandstone layer. That's the sandstone here behind me, contacting a basalt dike that has shot up from deep within the earth and cooled here. This is Prospect Point. There's other basalt dikes all the way down thing. There's a couple of them. As we walked up here, we saw a couple down there. But this is the contact between the particular basalt dike that formed the Prospect Point and the sandstone. We're at the older end of the sandstone. This thing here is the older side, because the sandstone's actually tilted, going that way, kind of that direction. So if this formed like that, here's a layer, here's another layer came on top, it was then tilted. So we're at the older end of it. As we work our way down there, we're going to see younger and younger rocks. Now, there's a major boundary between two very important layers. The
Cretaceous and the Tertiary. Also the Cenozoic and Mesozoic.
Cenozoic and Mesozoic. That was the voice of Thomas. He's here with me.
Hi, Thomas.
Yeah. So there's a major joint. We'll show that later. But up above me, we can see columbular basalts. And you just pan the camera out. You see them way up there. And those form because as the rock cools, it shrinks. And so it has to crack at some point. And it happens to be that the most efficient cracking method is hexagon. And so you get hexagonal formations forming way up top on the columbular basalts. Let's move on to our next location. Welcome back. Behind me now, we've moved a little bit further down. So Prospect Point's that way. The mountains are still behind us. And we moved a little bit further down to check out this actually really pretty rock face. We can see here, if glare would allow it, cross-bedding. Different layers, some sort of sedimentary thing going on here. We can see maybe some more cross-bedding. Even, and within these, there's magnetite. There's tiny grains of magnetite, and that's what gives it this darker color. We can also see down here some sort of vein or fault. It's some sort of oxidization feature because look at all the red in it. So we could have some sort of hematite or magnetite vein that's oxidized here. But you can see some of these cross-bedding features really well because the magnetite has settled into these. We're also younger. Down there, remember this whole thing's tilted. So this is younger rock now. This is even younger. We're starting to move more towards that major boundary, which is up above us somewhere. I'm not sure where. It may be eroded off the top, but somewhere, if the rock were to continue up, is our boundary. So we'll see you at the next location. Hi, welcome back. You might be able to hear that we are now in post because the wind noise was deafening. You couldn't hear anything I was saying. Now, what you can see behind me here is a little change in the sandstone. To the untrained eye, this may just look like a little change, but it's actually not. You can see it goes from a fine-grained sandstone to a more clastic and coarse-grained sandstone. Clastic meaning it has a little bit more pebbles and rocks in it. And what this means is that there could have been a change in depositional environment, meaning it would have gone from a sort of sandy Hawaii type beach to a more rough surf beach. Something like what we have now here on the west coast, where this is.
If you've ever been to Stanley Park, you'll know that there's a lot of rocks. What you can also see here, and what I'm pointing out here, is a little hill. What this could have meant is that there was a pause in deposition where sandstone would have stopped being deposited and it would have been eroded a little, and that would have created a little hill in the sandstone. Then the more classic and high energy, as they would say, environment with all the pebbles and stuff like that would have been deposited on top of this eroded layer, and thus there's a little hill in the rock. Now, what we're going to see in the next clip is the Cretaceous-Tertiary boundary. And you can see that this whole thing is tilted, and so it's a little ways down the rock there. It's actually somewhere above us, but it's just been eroded away a long time ago. We'll move down there in a little while, and we'll be able to see that there is actually a boundary in this rock. Hello. Welcome back. We have moved down now, and we are looking at what we believe is the Cretaceous-Tertiary boundary. We say believe because it didn't, the PDF we were looking at didn't 100% state where it actually was. But this is the most major line in the area, so we believe it. If you're confused about what I'm pointing out is, I'll throw up a little image here, overlay. And this is interesting because it's a very major boundary in geology. You're going from two different time periods. I had no idea this was right here in Stanley Park, of all places. It's kind of interesting how, people are walking right by it and they don't know that this is right here. Now, you'll note that it's tilted. In fact, the whole sandstone there is tilted. It's tilted because those mountains that you saw in the background lifted the whole sandstone up and slightly tilted it. Thus, all the boundaries and stuff within it are slightly tilted. Now, what you're looking at now is Siwash Rock. I believe that's how it's pronounced. I'm actually not 100% sure. It's another one of those basalt dikes. And essentially what happened is it was once a point, and water got in to cracks or weaknesses in the rock dike and broke it off. And now all we have is this little stump left of where that point once was. Now, the interesting thing is that this is basalt. The mountains behind me there are diorite. Now, diorite is actually this is actually granodiorite. Now, this diorite, specifically granodiorite, was created by ancient cascade-like volcanism, subduction zone volcanism. Now, this type of volcanism produces felsic to intermediate rocks like diorite and granite. That means they have more quartz and plagioclase and less hornblende and olivine. And this is true. We see that there's granodiorite here, but there's also basalt, and that's generally created by Hawaii type like hotspot volcanism or seafloor spreading volcanism. So it's interesting to find this right here where there's subduction zone volcanism. Why is this basalt here? I did not know that subduction zone volcanism could even produce basalt up until looking a little deeper for this video. So that's kind of interesting that it's here. This place is really interesting. Highly recommend checking it out if you have any interest and are nearby. I had no idea there was this much geology right here in Stanley Park. This is a tiny area. This concludes my first episode of BC Geology. Thank you for watching, and we will see you next time.